Now we're going to look at section 16.4, which is the number of signals. And this is going to deal with chemical equivalence. Now we discussed this in terms of carbon NMR when we looked at carbon in the fall semester. I'm going to explain it in a little greater detail as we look at proton NMR. So protons that have an identical electronic environment are chemically equivalent. They are going to produce one signal in your proton NMR spectrum. So the number of signals equals the number of chemically unique hydrogens. Your book does a very good job in this section, so I'm going to follow along with the book and just highlight what you need to know. 2 protons are chemically equivalent if they can be exchanged by a symmetry operation. So they're equivalent if they can be exchanged by either rotation or reflection. Let's take the example of propane that was in your book. If you have propane, you close your eyes and you rotate it 180 degrees. The molecule looks exactly the same as it did. So, the hydrogens that are circled in yellow are equivalent, and the hydrogens that are circled in red are equivalent. So you would have 2 signals in your proton spectrum. If protons are interchangeable based upon rotation, they are said to be homotopic. Homotopic protons are chemically equivalent. If you have trouble visualizing an axis of symmetry, you can do what's called the replacement test. And this will allow you to verify if 2 protons are homotopic. Okay, so we're going to be looking at these 2 hydrogens here. We're going to do the replacement test. where we substitute a deuterium for a hydrogen. You can see that these are the same compound. So the hydrogens are homotopic and chemically equivalent. Now if we take the example of ethanol, here when you have ethanol and you close your eyes and you rotate it by 180 degrees, you can see that there's a difference in the molecules. This is your alpha carbon and this is your beta carbon. So you can see actually now that the OHs have changed positions, and so have the alpha and the beta carbons. So you will not be able to tell by rotation if the two hydrogens on the alpha carbon are equivalent. These hydrogens are not homotopic. However, you can draw a plane of symmetry through the molecule. And you can see that if you reflect through this plane of symmetry and then close your eyes, you get exactly the same molecule back. Therefore, these two hydrogens are equivalent, and they are classified as enantiotopic. And they are equivalent through reflection. Once again, if you're having problems looking for planes of symmetry, you can do a replacement test. So if we take the example below that I have drawn, and we do a replacement test, you can see that we get a pair of enantiomers. So the hydrogens are enantiotopic. Unless specifically asked, you do not have to determine homotopic versus enantiotopic. You can just look to see if you have single bonds, and if you can rotate, would this lead to chemical equivalence? Okay, this is how we looked at it when we looked for carbons that were equivalent. You will have to be able to determine a homotopic versus an enantiotopic. But when you're just looking at spectrum, unless specifically asked, just look for chemical equivalence. If a replacement test fails, then the hydrogens are not chemically equivalent, and are considered to be Diastereotopic. As I said before, don't drive yourself crazy looking for rotational symmetry and planes of symmetry and axes of symmetry. If you have CH3 protons, the H's are chemically equivalent on that given carbon. CH2s are usually equivalent. Where it gets complicated is when you have a ring, and so there you need to look for chiral centers. And the reason why it gets complicated is because rotation around your single bonds is restricted in a ring. You also might see this restriction if you have double bonds. So again, don't drive yourself crazy. Look to see if you can rotate freely, and if you can't, then try and see if you can find rotational symmetry or reflectional symmetry, and you can always try your replacement tests. So this is going to conclude section 16.4.